Okay, welcome back, guys. Okay, let's talk about the basics of the ladder diagram. As you can see, this is a simple AC circuit. We have the 120 volt powering the lamp. So based on the truth table, you can see this is the all logic. Okay, those from digital background, we have digital background. So now this is the all logic. When we uh, turn on B, so what it means on is when this switch is closed, the lamp is on. Okay, and we have three possible way to turn on the lamp. One is the B on, A on, or both on. But when come to the PLC, we will do it differently. We will say when A is activated, lamp is energized. Okay, when A is activated, the lamp will be energized. Okay, we will use the word activate and energize to describe the input and output. Okay, then for the PLC ladder diagram, okay, we can actually convert this one so that it looks like a ladder. You can see now we have the two vertical line. You can also consider this as a hot. This is a neutral wire. So we go based on the concept of the current flow or the power flow concept, where the power will flow from the left to the right, okay, away from the left to the right. Okay, let me show you this. So imagine you have a power starting from here, and in order to turn on the pilot light, this switch need to be activated. So by the word activated, we mean the switch is closed. So when this push button is closed, the power can flow through the contact and therefore energize PL1. So PL1 is our pilot light 1, and we also can use another rung here, rung 1 and rung 2. We can use the rung 1, rung 2 as a path to turn on the PL1 like this. Alright, so before we begin, we have to understand the basic of the contact we use in the ladder diagram. Just because this is the ladder diagram, no doubt, but this is more like the switch and delay ladder diagram. For the PLC ladder diagram, we use only the contacts to represent input and outputs. So we don't really care about this whether it's a switch or whether it's the push button. Okay, everything will be replaced by the contact. So we have two types. One is a normally open. We call the normally open contact. The other one is a normally closed contact. You can see the difference. Here is a one line. Sometimes it's just a one cross line here, cross over from this contact to the other contact. And for the output, we just use a circle. Sometimes we use a bracket. Okay, so let's try to get this straight. So we have a normally open contact here. So when this normally open contact is activated, it's actually become closed. Okay, when it's not activated, it stays as open, right? So let's do the same thing for this normally closed. When this normally closed is activated, you change from closed to open. Okay, when it's not activated, it stays the same as the closed. Okay, you have to understand this before you can understand the actual PLC ladder diagram. So this is another way to look at the contact. First, we have the normally open contact. Okay, when this is the contact is de-energized. So the other word for not activated, probably you can say the de-energized. When it de-energized, it stay open. When it's energized, or another word we say activated. When this normally open is activated, you're closed. Okay, so for the normally closed one is just totally opposite. Okay, how they work is totally opposite. All right, let's look at this simple PLC ladder diagram. So why I say this is a PLC ladder diagram, because you see everything here, the input and the outputs are based on the PLC symbol. You see, on the input side, we can actually see the boundary. The yellow line actually draw the boundary, separate the inputs and outputs. So on the left hand side, we have all the inputs here, and then we put our output on the right hand side. Okay, and you can see unlike the previous one, we have the button. Sometimes we have the switches, but when we come to PLC, as I told you, we use only the contact, normally open and normally close, to represent the switches and push button. Okay, and what you need to know that for this diagram, you can see when you want to turn on, let's say, let's assume you want to turn on output Y. So what you need to do, if you there are a few ways you can turn on output Y. If you try to draw a current path, and if you follow this dotted line, is one of the possible way to turn on Y. You see when we activated when you activate E, F, and G, okay. When we activated E, F, and G, you can see the current can flow through the switches here. Sorry, the current can flow through the contacts here and go up and flow through the last contact to turn on the Y. So in order for the Y to be energized, we have to activate E, F, and G. This is the one possible way. Of course, the other possible way you can analyze yourself. Okay, let me tell you the other possible way is E, F, and H also. Okay, this is the second way. The third way is here. But for the round number 2 here, okay, for the round number 2, in order to turn on Y, we cannot activate this one since it's already closed. Okay, so we don't want to activate. We want it to stay closed so that the current can pass through it. Okay, one more time, we want C to stay closed. Therefore, we cannot activate C. C is not activated, but D is activated and G is activated. Therefore, we can energize Y. Okay, so this is how we analyze the ladder diagram through the current flows concept, or the power flows concept from the left to the right. Okay, here what you see here is the example of the PLC implementation, we call it, whereby we show the input module, how we connect the input module and how we connect the output module. Okay, in other words, how we connect the sensor to the inputs, how we connect the load to the outputs, and then in the middle here is our PLC program. Okay, first you should have to focus on the, let's start from here. Let's say we have one push button 1, externally it's called push button 1, but the PLC program wouldn't know what is PP1. Since this PP1 is connected to terminal 30, so we have to put 30 here so that the PLC program understand 30 is just normally open contact, like what you described here. And for the terminal 31, we have push button 2. Currently is normally open, so we use a normally open switch here. Okay, normally open switch here. And then as for the output, since this pilot light is connected to the terminal 40 of the output module, and then on this circle at the top, we have to name this one as 40 so that the PLC understand 40 actually refer to the terminal 40 of the output module. Okay, this is the correct way to implement the ladder diagram on PLC. So if you look further, we have one traditional or the primitive kind of ladder diagram they used since the 1970s. Okay, so we have this push button and limit switch. We have 2 limit switches, okay, to power this pilot light. You can see there is no PLC to implement this. So if we want to really implement this switch and delay circuit on the PLC, we actually need to put them on the we need to describe the sensor here. Sorry, we need to describe the push button and the switches here, how they connect to the input module, these three input module, these three terminal, and the load, how the load is connected to the output module. Okay, so I can see even though this is a come from a textbook, and somehow I don't think this is a correct way to implement the PLC. So for the reason that I told you earlier on, we actually need to use the terminal number like 30, okay, and we use the, instead of put PB1 here, which PLC cannot understand, we need to put 30 here, and LS1 is connected to 31. Let's name this one 31, and then we should, on the PLC program, this should be labeled as 31, because PLC, from the PLC point of view, from the PLC perspective, PLC only understand the terminal number, okay, because this terminal number is connected to the CPU, and the CPU understand it has a terminal 31. Okay, this way you need to put the terminal number here, and do the same thing for LS2. So LS2 is the next number 32. So this will be, let's use a 40 here. So this will be 40. Okay, this will be the correct way to draw the PLC implementation diagram. But this, however, we can still understand this simple diagram here. So you can see on the left hand side here, we have the hardwire kind of a system. On the right hand side, we have a PLC system. Okay, even though it's not based on the terminal, I think it's okay for the time being. You see, currently these three inputs are open, therefore there's impossible for us to turn on the pilot lights. Okay, and let's look at the scenario one. Scenario one, we have a push button one activated, but since the LS1 is not activated, and therefore pilot light cannot be energized, right? If you look at the PLC side, it's also the same thing here. When the PP1 is activated, so this 31 here, this, let's say this is a terminal 31, and then terminal 31 is activated, is closed, but this switch, this contact is still open, because here is open, so here is open. This is not activated, right? This is activated, this is not activated. So when this is open, there's no way for the pilot light to be energized. Okay, therefore, we can say that even though we have PP1 activated, pilot light cannot be energized. Okay, next, we turn on the, we activate PP1 and LS1, but also, since the LS1 is not activated, and the current cannot actually, current can flow through PP1, but current stop right here. Another current can flow through another path through the LS2, but the current also stop right here. Okay, LS1 doesn't allow the current to flow through, that's why PP1 cannot be activated. Okay, the same thing can be described with the PLC program. Okay, here we're using the contact. Here we're using the actual symbol of the push button and actual symbol of the limit switch. Okay, let's look at the scenario number 3, where we activated PP1 and LS1. Okay, right now I think you can see very clearly the current actually can passes through PP1 and LS1 to energize the pilot lights. Okay, same for this case also. Since both of the output, since both of the input device here are activated, and therefore these two contacts are also activated. Okay, so they become closed, and then the current can flow through to activate the pilot light. That's why the pilot light is turned on right now. Okay, let's look at the last scenario. The last scenario, we have LS2 and LS1 activated. So this provides another alternative path to energize the pilot lights, and same for this PLC implementation. So it's the same thing here actually. Only thing different is that we replace all this symbol with a contact. Okay, and this contact are follow the status of this input module. When this input is closed, inside contact also follow or close. Okay, and let's try to know the basic of the some rules that we need to follow when we are designing the ladder diagram. Okay, the first rule is you see that the output here, the label 10, and then on the input side, on the input normally open and normally close, also label as 10, and this is actually allowed. You can do that because on the actual relay, when the coil is energized, all the contacts in the relay will change their state, right? We have a normally open and normally closed contact in a relay. Okay, so they are all belong to the number 10. Okay, but some will prefer to label is a 10-1 or 10-2. Okay, to show that they are individual contacts inside this relay. Okay, by the way, this is okay for you to do that. You can name the output as 10 and then input contact as 10 also. Okay, this is allowed. And we'll see here. Now we have this implementation of the PLC. On the PLC, you can see this LS1 connect to terminal 20, and then on this PLC program, okay, we have some we have normally open, on some round we have normally closed, but on these three contacts they are named 20, 20, 20, the same name they use for this terminal. Actually, this is okay. Just like the previous case, it's possible to have using the same name for different type of contacts. Okay, inside the on the PLC program, is allowed to do that. On the next case here, we have the output labeled as 004, and then we have another input also labeled 04, and this is allowed, right? So how do we understand this? When this coil is activated, 004 coil is activated. Okay, since this is dependent on the 04, they have the same name. Therefore, when this energized, this is activated and it close. Okay, okay, the contact will close. Okay, when the this output coil is activated. All right, let's consider another ladder diagram. Can you see anything wrong with this ladder diagram? Can you see any error with this ladder diagram? Okay, so the problem actually lies on the output 1. You see, this output 1 is energized. On means energized, right? Because we have A on, B activated, and C activated. We have these three switches activated. We have these three contacts activated. So the power can flow from A through B through C and energize the output 1. But on the separate round here, on the round number 3, this contact is activated, this contact is activated, this contact also activated. But the most important one in series with these three, this one is not activated. Therefore, the output cannot be energized. But the problem is not lies on this round. The problem is lies on the this output name here. You can see for the point of the PLC, from the perspective of the PLC, if you tell the PLC to turn on output 1 and also turn off output 1, so which one is correct? You want the PLC to turn on output 1 or turn off output 1, since they are both happening at the same time simultaneously. So there's of course there's no way for the PLC to do that, to on and off at the same time, right? That's why if you really want this to be if you really want this input to associate with the output 1, you really need to combine like this, draw a vertical line and remove this path and remove this output. Okay, so this input will join with the with the one up above it to control output 1. Okay, so this is the correct way to do this. We remove the path and remove the output 1. We just use only one output 1. Okay, so there will be no conflict. Just like this one, you will not have this conflict when this on and this run is off. Okay,